Hey, what's up everyone? Welcome to Stoichiometry/Solutions Part 1. Today we're going to be talking about moles, molar mass, and chemical equations. One of the most fundamental ideas of stoichiometry is the idea of a mole. And the mole is going to come up all throughout chemistry, so it's really important that you have a good understanding of what a mole is. And a mole is just a number. It's Avogadro's number. It's 6.02 times 10 to the 23rd. Now, a mole works very similarly to how a dozen works. A dozen represents 12. So you can have a dozen eggs, or you can have a dozen pencils. A mole works similarly. You can have 6.02 times 10 to the 23rd of an atom, or a molecule. So really the only difference between a dozen and a mole, or Avogadro's number, is going to be the size. So a mole is many orders of magnitude greater than a dozen. And the reason for this is because when we're talking about a microscopic level, when we're talking about molecules and atoms, we need to be talking at these types of scales so that us as humans, we can represent them in ways that we can kind of fathom. And one of the ways that we use a mole to do that is by talking about molar mass. So the molar mass is the mass of 1 mole of a substance. So for carbon, 1 mole of carbon is going to be 12.01 grams. And if you ever want to find out the molar mass of a element, you always look at the periodic table. So in the periodic table, you're going to have the chemical symbol. In this case, for carbon, it's C. On top of it, you have the atomic number, which represents how many protons are in that atom. And underneath that, you have molar mass. Now, this molar mass is kind of 2 values. First of all, it's 12.01 atomic mass units. This represents the mass of 1 atom. And it's in the unit of atomic mass units, AMU. And AMU is a very small percentage of a gram. But the atomic mass is not really as important as the molar mass. So the molar mass is 12.01 grams. So 1 mole of carbon is going to weigh 12.01 grams. Now, molar mass for a compound is going to work very similarly to molar mass for an element. So let's say I give you the compound CH4, methane. In order to find the molar mass of this, you add up all the molar masses of all the elements. So what do I mean? Well, carbon here has a molar mass of 12 grams. And hydrogen here has a molar mass of 1 gram. But you have 4 of them. So you have to multiply this number by 4, and then you add them up, and that gets you a molar mass of 16 grams. So CH4 has a molar mass of 16 grams. 1 mole of methane is going to weigh 16 grams. Let's do another one. Let's do carbon dioxide, CO2. Carbon is going to weigh 12 grams, and oxygen is going to weigh 16 grams, or 1 mole of oxygen is going to weigh 16 grams. And since you have 2 of those, you multiply that by 2. So it's 12 plus 32, which is 44 grams. 1 mole of carbon dioxide is going to weigh 44 grams. And that's how you find the molar mass of a compound. Another reason why a mole is really helpful is because it helps you relate mass to particles. So if I give you a problem like how many carbon atoms are in 24.02 grams of carbon, that problem becomes really difficult if you have no understanding of what a mole is. But when you do know what a mole is, you realize how simple it is. So first of all, we want to convert grams into moles. So we have 24.02 grams of carbon, and we know that in 1 mole of carbon, it's going to weigh 12.01 grams. So really we're dealing with 2 moles of carbon. And now since we've converted mass to moles, we can now convert moles to particles. So we have 2 moles of carbon, and we know that in 1 mole you have 6.02 times 10 to the 23rd atoms. So you have about 1.2 times 10 to the 24th atoms of carbon. And so using our understanding of a mole, we were able to convert grams, or the mass, into the number of particles. Another thing that the mole is really helpful for is talking about concentrations. So we have 2 different units of concentration, and we'll talk more about this in solution chemistry, but we have molarity and molality, and both of them use moles to represent the concentration of a certain solution. Now, it's not really important for you to know molarity and molality in much depth right now, but I just want you to know that they are used when talking about concentration. So the big takeaway here is that a mole is really, really helpful and it's really, really important. And you'll definitely be using a mole throughout all of chemistry. All right, now that we've talked about the mole, let's talk about chemical equations. But before we can really start talking about chemical equations, we need to talk about what a chemical formula is. A chemical formula is a way of representing the number and types of atoms present in a molecule. And you've definitely seen chemical formulas before. For example, things like water, H2O, and carbon dioxide, CO2, are examples of chemical formulas. And all they're telling you is that, for example, in one molecule of water, you're going to have one atom of oxygen and two atoms of hydrogen. And similarly, in carbon dioxide, all that's telling you is that you have two atoms of oxygen per one atom of carbon. Now, a thing about chemical formulas is that unless a charge is stated, the net charge is assumed to be zero. But there's compounds where that isn't the case, and we call those ions. So an ion is an atom or a molecule with a net electrical charge. And there are some examples of this here. We have acetate, ammonium, carbonate, cyanide, hydroxide, sulfate. These are by no means a comprehensive list, but these are some examples of what an ion looks like. These are called polyatomic ions, and there's a whole list of common ones that might be worth memorizing. But you also have atoms on their own being ions. For example, if you have something like Na+, that's an ion. Cl-, that's also an ion. But you can kind of see how there's two different types of ions. First of all, we have ions with a negative charge, like the acetate or the chloride. And these are what we call anions. Anions. And on the other hand, we have ions with a positive charge, for example, ammonium, and those are what we call cations. So, although they're both ions, they're named differently based on whether or not they have a positive charge or a negative charge. Now, we can use our understanding of chemical formulas and also apply our understanding of a mole to solve problems. For example, if I asked you how many hydrogen atoms are in 64.2 grams of NH3, we would need to use both our understanding of a chemical formula and our understanding of a mole to solve this problem. One of the first steps that we're going to need to take in order to solve this problem is first converting grams to moles. And the way we do that is by dividing by the molar mass. So let's first determine the molar mass of NH3. So we have NH3, nitrogen has a molar mass of 14 grams, and hydrogen has a molar mass of 1 gram, but we have 3 of them, so that's 3 grams. 14 grams plus 3 grams is 17 grams. So the molar mass of ammonia is 17 grams. So let's use that information. We have 64.2 grams of NH3, and we know that in 17 grams of NH3 is 1 mole of ammonia. So that's going to come out to about 3.78 moles of ammonia. And now, although we found moles of ammonia, we're going to need to somehow relate this to moles of hydrogen. And the way we do that is by looking at the chemical formula. The chemical formula of NH3 tells you that for every 1 molecule of NH3, you have 3 atoms of hydrogen. And by similar logic, in 1 mole of NH3, you're going to have 3 moles of hydrogen atoms. So if you take this number that you got here, 3.78 moles of NH3, and you multiply it by the conversion factor, so 1 mole of NH3 is going to have 3 moles of hydrogen, you'll realize that we have 11.3 moles of hydrogen. But of course, the question doesn't ask us for moles, it asks us for hydrogen atoms. And so this is where we need to use our understanding of a mole. So we have 11.3 moles of hydrogen, and we know that in 1 mole, you have 6.02 times 10 to the 23rd atoms. And this is coming from from Avogadro's number. This is coming from our understanding of a mole. And if you do this calculation out, you'll realize that we have 6.82 atoms of hydrogen, and that is your answer. And so this problem kind of exemplifies how you can combine your understanding of a chemical formula and your understanding of a mole to kind of solve these types of problems. One more note about chemical formulas before we move on to chemical equations is that you're going to have two different types of chemical formulas. So the first type that we're going to have is something known as the empirical formula, and that's going to be the simplest positive integer ratio of atoms. We'll see an example of this, but let's talk about the other one really quickly. So the other one is going to be the molecular formula. And the molecular formula is going to be the accurate proportions. And so to kind of get an understanding of this, you have to look at an example. So let's look at glucose, which is C6H12O6. Now, this chemical formula is the molecular formula. And that's because if you look at a molecule of glucose, it's going to have 6 atoms of carbon, it's going to have 12 atoms of hydrogen, and it's going to have 6 atoms of oxygen. But if you look at the ratio of those numbers, the ratio is 6 to 12 to 6. That ratio can be simplified to 1 to 2 to 1. And so the empirical formula of this compound would be CH2O. That's the empirical formula. So empirical formula is the simplest positive integer ratio of atoms. The reason we have empirical formulas is so that we can get an understanding of the ratio of atoms without having to look at their actual proportions. So in a lot of compounds, their proportions are going to be really big. The subscripts that they have are really big numbers. And so the empirical formula kind of simplifies all that down and helps you look at the actual ratio of atoms and the types of atoms that are found in the compound, not necessarily the accurate proportions of them. All right, let's finally talk about chemical equations. So a chemical equation is a method of representing a chemical reaction where some reactants turn into products. And you have an example right here. So you have methane reacting with oxygen to produce carbon dioxide and water. This is the type of reaction that we call it a combustion reaction, and we'll talk about types of reactions later in a different unit. But this chemical equation is telling you that methane reacts with oxygen to produce carbon dioxide and water. And you might notice something weird, and it's that in front of some of these numbers we have a coefficient, and in front of other numbers we don't have a coefficient. So why do we have a coefficient on some chemical formulas and we don't on others? And the reason for this is that in a chemical formula, all the atoms on the reactant side must be present on the product side. So if we look at the reaction without those numbers, let's have CH4 reacting with oxygen to produce carbon dioxide and water. If you count up all the elements on the left-hand side and all the elements on the right-hand side, you'll notice that something is wrong. So let's do that really quickly. We have 1 carbon on the left-hand side, we have 2 oxygen on the left-hand side, and we have 4 hydrogen on the left-hand side. On the right-hand side, we have 1 carbon, we have 3 oxygen, and we have 2 hydrogen. So clearly something is not adding up. And we need to make sure that all the elements found on the left-hand side must be on the right-hand side. So what we do to make that happen is that we add coefficients in front of certain chemical formulas. So in this case, we add a 2 in front of the water and a 2 in front of the oxygen. And you'll notice that everything kind of works out. So now instead of having 2 oxygens, we have 4 oxygens. And on the right-hand side, instead of having 2 hydrogen, we have 4 hydrogen. And instead of having 3 oxygen, we have 4 oxygen. And now everything lines up. What we did here by adding those coefficients in front of certain chemical formulas is something known as balancing the equation. So let's get a bit of practice balancing another equation. Let's look at carbon dioxide reacting with water to produce glucose and oxygen. So first of all, let's do a tally of how many elements we have on the left-hand side and how many elements we have on the right-hand side. So first of all, we have 1 carbon, we have 3 oxygen, and 2 hydrogen on the left-hand side. And on the right-hand side, we have 6 carbon, we have 8 oxygen, and we have 12 hydrogen. So clearly this equation is not balanced. So we need to do something to make it balanced. There are a couple of tricks to balancing a chemical equation. And probably the most helpful one is to look at which element has only one source. If you look at the left-hand side, the only source of carbon is the carbon dioxide, and the only source of carbon on the right-hand side is the glucose. And since there's only one carbon here and 6 carbon here, you know that the coefficient that goes here must be 6. Another easy one is the hydrogen. So the only source of hydrogen on the left-hand side is the water, and the only source of hydrogen on the right-hand side is the glucose. And since there's a subscript of 2 here and a subscript of 12 here, in order for these to be balanced out, you know that you need a subscript of, a coefficient of 6 here. So now let's do another tally of what we have so far. So on the left-hand side, instead of having 1 carbon, we have 6 carbon. And instead of having 3 oxygens, we have 18 oxygens. And instead of having 2 hydrogens, we now have 12 hydrogens. Let's do the same thing on the right-hand side. So we still have six carbons, we still have 8 oxygens, and we still have 12 hydrogens. So the only thing that's not really adding up here is the oxygens. We know that glucose is contributing 6 oxygens, so the rest of the oxygens must be coming from the O2 here. So we're going to need 12 oxygens, and therefore the coefficient that goes here is also a 6. So your final balanced equation becomes 6CO2 plus 6 water produces glucose, H12O6, plus 6 molecules of oxygen. And that is your final balanced equation. And that's how you balance a chemical equation. So there are some techniques, but a lot of it is just going to be trial and error until you just get, a set of ratios that kind of work. Okay, that's all I have. Thank you for watching. I hope you were able to learn something, and I hope to see you later. Thank you.